Okay, so I will continue yesterday's some of the discussion. Okay, so yesterday I started to, so we discussed genetic drift, and I started to discuss about mutation and drift. And we were doing this one locus model in which we said A1 can become A2 with some probability mu, or A2 can become also A1 with same probability, same mu. Okay, and I was asking you, how does the distribution of these A2s look like in the large times, right? And I saw that, looking at your notebooks, you guys are making very nice effort to look at the dynamics of it, how these stochastic trajectories look like. Okay, so I just wanted to clarify that point because I don't think that has been sort of discussed, or or how will it look. So let's just go through that once. Okay, so we have, so let's first start. So I want to just clarify these 2 points about dynamics and what we said about mutation drift balance. So let me just explain this point. So suppose I have this, I just generated these trajectories. I wrote a little program and generated these trajectories to some parameters. So let's say n is 100 and mu is 10 to the power minus 3. And I'm plotting the frequency of A2 as a function of time. So that's what I saw in notebooks people were trying to do yesterday, right? So you expect that, suppose I started no A2s, 0 A2s, okay? Started with 0 A2s, then what happens? So, although I started with 0 A2s, they will be generated from A1s, right? And they do something, and then perhaps they get sort of quasi-fix. Quasi-fix because, they can reach a frequency of 1, but then mutation will happen, and then A2 can become A1 back. So this is what they will do. Okay, so it's not an oscillation. Oscillation is a more periodic thing. So it's just a fluctuation. So this is what they will do. Okay, this sort of thing. When the mutation is small, does this make sense? Mutation is not 0, it's tiny. So it's almost like fixation, but it's not fixation because you can reach this absorbing state in which all are A2s and none of them are A2s. So it will keep moving between these 2 extremes. Okay, so some of you were trying to plot this sort of thing yesterday. But let's look at this other case in which n is, say, 100. Again, but mu, let's say I took 0.05. In this case, what happens? So again, I start with 0, okay? And then it fluctuates, and then it does something like this. Something like this. Does this make sense? So n is somewhere here. And there's some number about which is fluctuating. So first of all, I want to say this point about when you said long times, what does that mean? There is a transient, initial transient here, this part, okay? And after that, it's fluctuating, it's still changing with time, okay, about some constant. When we're talking about mutation selection balance, mutation drift balance, etc., time is out of picture, right? So what one is saying here is that if I generated lots of such trajectories, at long times, if I take, suppose, the mean, that will become independent of time. So I generated lots of such trajectories, and I look at mean frequency of A2, then it looks something like this. It does not fluctuate, it's a constant in time, whereas each trajectory will fluctuate. Okay, so just get this word clear. When you're saying balance or equilibrium or stationary state or steady state, this is what we mean. Things have become constant in time. Okay, not only the mean, variance, etc., the whole distribution becomes constant in time. Okay, so now you can look from the dynamics point of view, And that's what we were trying to do, but that's a little hard. Okay, so if you tell me to, learn about distribution from liquid dynamics, at least I will find it hard. So I want to tell you, it's a good idea. However, forget the time now. Just don't think of it, how it came and so on. Just go directly there. But understand the time is not there in the sense that things have become independent of time. That's what we mean at large times. Okay. Okay. So now a simpler way of thinking about or answering the question that I was asking you yesterday is to think of extremes. So in fact, Mike demonstrated that yesterday for effective population size. So that's a very good way of thinking about when you have a new question. Think of these limiting cases. So let's take, first of all, the case when mu is 0, we know. We spent a lot of time yesterday discussing that. But mu is now tiny, say 10 to the power minus 4. And I'm asking that if you collected statistics from here, how many A2s are there? Okay, so it will keep doing this all the time. It is not going to become constant like this guy. The mean will still become constant here also. Okay, but if I take statistics from here, how do you think the distribution look like? Okay, so I will tell you. So I know that when mu is 0, it was just these two sticks right here. This stick and this stick, right? Because like the Buri's experiment we saw. But now because of mutations, the weight is not 1 here. It's slightly less. Okay, because we will also generate, our statistics will also contain these frequencies. It has to go from here to here, right? So these frequencies will also click. So this distribution, therefore, looks something like this. A U-shaped distribution. Does this make sense to people? Yeah, okay. So I'm saying that when mu was 0, we had these two sticks, right? Either you have, with half probability, you have 0, all the A2s or no A2s. But because of mutations, very tiny mutations, once in a while mutations will happen, because of which you are not exactly at 1, you are just slightly below and you're just fluctuating, a little bit like 0.99, 0.98, something like that, right? So you're not going to become exactly 1, you will become 1, but again, it will become 0.99, 0.98. So therefore, it's not going to be exactly 1, but there is some weight of the distribution close to 1. Similarly, on the other side. And when it's making these transitions between 0 and 1, you will also sample these intermediate frequencies. And that's this part. Think about it again. Okay, so again, start, however, from mu equal to 0, and then turn on the mutation teeny weeny bit, and then see how it looks like. Okay, but that's how the trajectories would look like. Okay, so start from that extreme. What about mu when it's large? So let me just take this extreme here, and we did not speak about this, so let me just do that now. So now let's take the other extreme in which mu is high. And just to simplify problems, the extreme I'm taking here is to say that the size of the population is large. So that fluctuations, as we learned yesterday, drift can be ignored, and therefore I can think of only mean. Okay, so let me just explain to you. Therefore, so I said that it fluctuates about some constant. Can you guess that constant? Can you think of that constant? What that constant might be about which is fluctuating? Any guess? Okay, I'll tell you. So suppose the frequency. So we're not thinking of, again, this dynamics. But suppose the frequency of A2, if this large times that white curve is some f, okay? And therefore frequency of A1 would simply be 1 minus f, right? Because either you are A2 or you are not A2, right? Okay. So then here the balance means that this A2 will lose the frequency of f will reduce. It will lose with mu f because it's mutating away. That's the loss it's getting, right? The things are becoming A1. So that's the loss from it. But I told you how it will gain also, right? And how will the gain come? What will be the gain to it? This is the loss in the frequency due to mu, and the gain will be mu 1 minus f. That's right, very good. Right? That will be the gain. And now I said these things are independent of time. How will things become independent of time if whatever I give you, you give me back? Same amount, right? So therefore things, whatever money you have, I have, I mean, it remains the same. And therefore, these two are balancing. Okay, so that's what we mean. Okay, you can write a little equation also, df by dt and so on, in case, you know, this is how you think. So you can write like this. So this is basically what one writes down and then says that df by dt is 0. So those who like to write equations, okay? But that's basically the idea here. And therefore, what is that frequency f? Where it's satisfied? Huh? Yeah, so because, yeah, they're very large times and I'm looking at mean. So this is this mean frequency. The f is the mean frequency, sorry. Should have written it better. Yeah. Okay, so time is there, but you know, the balance here means that the certain things have become independent of time. So therefore, what frequency will this be satisfied? 0.5, right? So that's it, finished. N by 2. Okay, so it's fluctuating about frequency mean. This frequency mean is half, and therefore now let's again join the dots. So now this distribution is function of this frequency. So here, sorry, this I mean the average here. Okay, so now this is centered about half because the mean, but because you know I assumed it's n is very very large, but actually n is small. I mean you know it's finite, so therefore there's some width. So it looks something like that. So that's the distribution here. Very low mutations, it's almost, it's quasi-fixation. It has a lot of weight near these boundaries, okay? But as mutations increase, there's this balance because of which you have this things centered in the middle. Okay, so there's a very, I mean, I like it, it's very cute. And this distribution is changing its shape. And in fact, this distribution is very well known. I'll just write the formula for you. Okay. So for 2n mu, so more precisely, this is the situation when 2n mu is less than 1. And this is the one when 2n mu is large than 1. So it's called beta distribution. And as 2n mu switches from less than 1 to greater than 1, there's a nice shape change from U shape to sort of something like a Gaussian. Okay, and note that the answers are not depending only on mu or only n. It depends upon this combination of n and mu. And that's coming from diffusion theory, the way certain things called scalings are done. Okay, so it depends on this parameter, composite parameter. So this will you will see again and again. So n mu, and sometimes we use these words like if this is the one, this is called weak selection. Sorry, I'm sorry, weak mutation. So weak, that means relative to drift, because mu is smaller than 1 by n. 1 by n is a measure of drift, and this is called therefore strong mutation. Okay. Okay. So please think about it again. First time if you see, it's a little hard, but I think after a couple of times you get used to it. Okay. So this is what we were discussing yesterday. And now I want to go from one locus, because it's kind of boring, to a different case in which we have lots and lots of loci. Okay. And in that context, I want to describe a new sort of a standard model. But let's see how it goes. Okay. So the question that I'm interested in is understanding, I mean, like everybody else, how about the diversity in a population. Okay, so let me describe this point. Okay, so let's look at some made-up data. So suppose I have this data in which I have lots of loci and 6 individuals. So I'll give you some data and we will do some numerical problem for a while. So these are the loci and these are the individuals. And there are lots of loci. So earlier, what I did yesterday and today morning, we were just looking at one locus, just one locus with 2 alleles, right? Okay. So now I want to look at lots of loci. 4, 5, 6, 7, lots of them. But I'll write only 8. And this is a sample somebody gave me today. So they said this first individual, 6 to 6 individuals, and first individual has no mutation. It's a wild type at the first locus. Second locus, it is the mutation, and so on. So let's say this is the kind of data we have. And we will do a little numerical exercise with it. Let me fill it in. And I want to calculate, learn how to calculate, let's say, pairwise diversity. Anybody wants to tell me what that is? Okay, done. Okay, so I would like, so this is the data. And let's try find by pairwise diversity, at least a part of it. So pairwise diversity means I just take 2 pairs, say 1 and 2 sequence, and wherever they are different, I count how many loci they are different at. So this is also called Hamming distance. So the differences are how many? 1, 2, 3. That's it, right? So 3. So this is between 1 and 2. What about 1 and 3, 1 and 4, 1 and 5, 1 and 6, 2 and 3, 2 and 4, and so on? Okay, so let's do at least a part of this exercise. Can you please tell me 1, 2, 1, 3, 1, 4, 1, 5, 1, 6? Can you calculate those parts for me? 3 plus 1, 3. How many loci are they different? 2, 2. Yeah. 1 and 4. 3. Okay. 1 and 5. Everybody understands the question? You just have to compare and see, are they in the same state, if you like? Right? These two, 1 and 4, they're in the same state here, not 1 and 0. So that's 1 click. Same. 2 clicks. 3 clicks. Right? That's all for the fourth one, the 1 and 4 pair. Yeah? It's a simple one, simple thing, right? Everybody understands? Yeah, okay. So you can fill this in at home. Okay. And I want to find the number for this. It's a mean pairwise diversity. And so I'm going to compare 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 3, 2, 4. How many such pairs am I forming? How many pairs can you form? Huh? Count and tell me. How many pairs can we form? 32. 32. No, be careful, should not overcount. So if you have done 1, 2, don't do 2, 1, it's already done. So non-repeating. How many pairs? 15, very good. That's correct. Why 15? Anybody wants to tell me, suppose I had given you n individuals, how many pairs can you form? And choose 2. So you saw this funny looking symbol yesterday in binomial distribution, right? Okay, yeah. So that's 6 chose 2 and that's 50. Okay, and so averaging over all these pairs, and I have 8 of them. So you can put this number. So it's just a number. It's just to get you started. It's nothing like great here. 45 by 120 is what I got, but this is a small exercise. Please work it out at home. Okay, and see if maybe I made a mistake. Okay, so the question that one is interested in is that, okay, you have this data, and the big question is, what is this number? Like, what can I say about this diversity it's showing me? It's a measure of diversity, right? If all the sequences, for example, 7th locus, they're all identical. So therefore, you will get a 0 from here, right? It does not contribute, right, to the diversity, right? So what are the underlying evolutionary forces which are determining this diversity? What evolutionary forces are shaping the diversity? So that's a big question in the subject, right? Okay, so one would like to understand that. So a commonly used model to model such data is called the so-called infinite sites model. So, Kimura, 1969. So it says, suppose initially I have this lots of loci. So it's assuming that the sequence is very, very long. Okay, and let's say all sequences are wild type. So 0, 0, 0, all of them. Okay, so 0 can become 1. So now we are going to introduce mutations and other forces perhaps. Okay, so now 0 can become 1 and 1 can become 0. But this sequence is very long. So if already I have a 0 somewhere at some locus, it can become 1, yeah, okay. But the same locus is chosen again to have another mutation. That means 0 has become 1, and then this 1 can become 0 in principle, right? But the chance that the same locus is chosen to make a mutation, that is negligible if the sequence is infinitely long. Does it make sense? How much is that probability? Suppose the sequence is L, long, is the length is L. What's the probability that I will hit the same site twice? 1 by L square, right? Because L is very long, so therefore it's unlikely that I'll hit the same site. So 0 can become 1, but that's it. You've chosen it once. And 1 can become 0, but no, we're not choosing the same site again. So it assumes that mutations from a mutation occurs at a locus from 0 to 1, and it's an irreversible mutation. Because it's an infinite sites. That's the assumption. People, make it more sophisticated models saying it's finite and so on. One can do that, but this is more or less, the things work out pretty well. Okay. And second thing it assumes is that the recombination is high. So you heard about LD yesterday. So I'm not sure if you saw the formula. It decays very fast, exponentially fast. So maybe I think Sally will do that. Okay. So I'm assuming this rate at which recombination occurs is very large. So therefore LD decays very, very fast. So I'm not going to worry about those associations. Okay. So I'm going to ignore LD completely because recombination is assumed to be high in this model. Okay. So therefore all of these loci are just going to evolve independently. So what do we have? Let me just repeat this point. So there is this locus 1, 2, 3, 4, and so on. At locus 1, for simplicity right now, there is this one mutant arrives. After that, you just turn off the mutation. No more mutation. Once a 0 has become 1, that's it, finished. And after that, you just let it do whatever it wants under the action of drift. Okay, that's basically the model. Second locus, also, just once a mutation arrives, and then it just sits around and does its drifty thing. Okay, does this look like an interesting model? When I saw it first, I was like, does this sound like an interesting model? There are lots of models, but they have to there should be sufficient play in them, sufficient interesting in them, no? Does this look like an interesting model to you? We know everything about single locus, right? You tell me that, at time t, I can tell you how many mutants, what probability is there of getting n mutants because of the diffusion theory or by simulations. I can tell you that. So each locus is doing its thing. Is it interesting? Should we? No, lots of people work, everybody works in this model. I mean, almost everyone. Isn't it? Yeah.
Okay, I mean, not the question answered question whether it's interesting or not, but I have a question. So the assumption that the site will not mutate again, I guess it also depends on the time scale at which the problem being time scale at which the problem being looked at, right? I mean,
yeah. So time scales are, so mutation rates are small enough, or therefore okay. Time scales are large enough. Yeah.
I see.
So, but I mean, I think here it's more. It's about L is large enough. Okay. That you don't hit the same site twice. But your mutation rate is large enough, then of course you will. Okay. So time scale is also large.
Thank you.
Okay. So just, we love models, but it's such an interesting model. Anybody wants to give you thoughts? At least I thought it was not very interesting initially, but of course, Okay, so I think it's not a bad model in the sense that it's an interesting model. So there are a couple of things that we should sort of realize. So you see that although I said first locus, one mutant comes, and then only drift, we can add selection also, other things also. Okay, but because it's a single model, and we know a lot about single locus, right? So the first mutant and the first locus, mutant came, and then it's doing whatever it wants to become. N. Maybe fakes or not, or whatever you like. Okay, maybe it does this. But at the second locus, mutations will come stochastically. They're not starting the same process, this process at the same time. Okay, so at the second locus, perhaps, so this is my first locus, and this is the second locus. At some other time, so this is the time axis. Okay, and this is the frequency in the trajectory of A2. Okay, this will come at a different time. So each of them has they have a different clock. So there's a global clock, but each locus has its own clock running, which starts at a different time instant, right? So these mutations are going to come stochastically. So maybe this one comes, and then maybe something it does, and then the third one, and so on, right? So, okay, right? So let's first of all note that. Secondly, the kind of questions one is asking. So everything is one locus. You can ask questions which require you to look at all the loci simultaneously. In that sense, it's a multi-locus statistics. So the kind of question that one asks is, for example, I want to know how many segregating sites are there in this sample, in this example. So today you gave me the sample, which means at this time instant, this is my time. I'm looking at all these processes that started at different times, whatever this is doing, right? And I want to know how many segregating sites are there, right? So in that sense, I have to look at each of them together, right? So in that sense, it's still an interesting multi-locus statistics. So what's the say, and how many segregating sites do we have in this example? Segregating sites means they have not got fixed. So not every locus, this is segregating, right? Because there are zeros and ones, it has not got fixed or extinct. So how many segregating sites we have? 7, right? Only this one is the sort of the not. Rest are all segregated, right? So it required me to look at the same instant, all the loci together. Okay, so therefore, it's still interesting model, and one can ask non-trivial questions in it. So one of the questions that one asks is something called SFS. So let me elaborate that a bit. So it's called site frequency spectrum. Or SFS. So let me define this for you. So SFS, let me define it, I'm denoting by Fn. It's the mean number of segregating or polymorphic loci we can put F and T also. Okay, with N. That's the definition of SFS. How many loci, segregating loci do you have? Average number, because this is a sample. we have to average it. Either you give me more samples, or I have tons and tons of loci. So in that sense, I can do the averaging. Okay. So, but that's how, for example, if I were to run simulations, I will do lots of such. I will do this one, and then I will repeat the process, and then I will average it over. Okay. And then in that sense, I can get the mean number of loci. So that's the kind of question that one is asking, right? At time t. So let's, for a second, we'll remove that. Is that question clear? What's the meaning of this object called SFS? Average number of loci. Average we cannot take from the sample, but maybe you can plot this SFS for me. Can you do this exercise, please? F of n versus n. Let's try it. Can you find the number of segregating loci which have n mutants? So mutants here are ones. It'll take you, I think, 3 minutes. So take the time. And again, feel free to chat. So how will we go about doing this exercise? Actually, take your 3 minutes. I think it's good to think on your own before you get the answers. So try it yourself and please chat with the neighbors. Yeah. Okay, let's look at it. How many loci have six? So we cannot have 6 mutants because that's uninteresting. We want polymorphic loci, right? So how many loci have 5 mutants? How many have? Okay, let's start like this. How many loci have 6 mutants? 1, correct. How many have 5 mutants? None. Yeah, so you have the answers, right? F5 is 0. Very good. F4. How many loci have 4 mutants? 1? Which one? None. F3, 1. F2, 1. Two. This one and this one, right? Yeah. And F1, 3, 3, 4. Okay. Yeah, that sounds about right. Yeah. Okay. Can you plot it? Let's forget that we have softwares. I mean, softwares are sometimes hateful things because everybody just dumps it on some software. Just do it with pen and pencil. Let's try it. Please plot that histogram for me. Histogram. How does it look? One, two, and three. How many can we have? 5. You know, we have to draw these bars. Remember, bar graph, I think it's called maybe. So F3 is equal to 1. And F2 is 2. And what did you say? F3, F1 is 4. Okay. Okay, that's the histogram. Correct? Yeah? Right? So that's what the statistics of SFS will look like if you're giving me the sum. Correct? Yeah? Okay. So what is it, showing? It's showing that SFS is, here it's nothing here, 0, 0. Right? Okay. So it's decreasing. It's a decreasing one. This FFN is decreasing with the number of mutants. Right? Okay. So you received this paper for this fancy journal with a lot of impact factor. And this person is claiming that their data is consistent with neutral theory. That's the question, the big question that we were asked, right? What is shaping the diversity? Okay, and this person is claiming this. So it's a hard question actually, because what you can say is that it's decreasing, yeah, but there could be many scenarios, many possibilities which may be consistent with this pattern. So more precise question is that this is one of the plausible scenarios. So this person is claiming that a plausible scenario for this data is that this population was under genetic drift only. It's a neutral evolution. So what do you think? Would you pass it? My paper, by the way. What do you think? So this requires only something about genetic drift. Again, think in chat, please. Let's go. Let's do that. 2 minutes chat and tell me pass or fail.
Again, repeat the question.
Yeah, I'm asking, is this pattern of the SFS consistent with neutral theory? That's a question. So whatever you have learned, I think it will be very helpful to test this, to answer this question. Please chat. It's saying that there are fewer loci with larger number of mutants, right? That's the sort of verbal interpretation, or verbally, if I say. So there are more loci with few mutants, right? And fewer loci with more mutants, right? Does this make sense? Right? Is it consistent? Is it what you would expect? Sorry to be so hard on you, but I think it's okay. We'll do it. It's fine. Okay, so I would say that yes. Why? Because it at least looks plausible to me. Because you see, your process is starting at one mutant, right? The things that we saw yesterday, you were starting with half population of mutants, right? And I said it will just remain constant and so on. But this is one guy. Its fixation probability or reaching, or rather establishment, that means it reaches high enough level so that it doesn't get lost. That is very low, 1 by n, right? Okay. So most of the time, this one guy will get lost. Most of the time, if you run the simulation, right? So that's our intuition. There's this one guy in this large population, and therefore, it will just get lost. And therefore, very few I will see. Most of the time, I will see something like this, right? Most of the loci will have very few mutants in them, and most of the loci will have very few mutants, and most loci will not have it, right? Okay, so the answer, so this is only qualitative, and you have to do more work than this. And so that's where this infinite sites model comes to play. So because we know a lot, all nasty formulas that you can do using this diffusion theory. So from all that stuff put in together, we know that if we have a neutral answer, then this f of x being the frequency, that's given by this formula. It's n times the neutral mutation rate divided by x being the frequency, n by. Okay, so it's a nice simple answer. It decays. So I've been showing you things like exponentials, e to minus x, things working very slowly. 1 by x decays is a pretty slowly decaying function. Okay, so that's a sort of famous answer. I should point out here that although I tried to make it plausible using fixation probability, this calculation actually requires something much more involved, which is called sojourn time, which is about the time spent at a frequency x. And we don't have time to discuss time. And it's a pretty long thing and involved thing, so that's why I'm not doing it. But at least be aware that this formula is coming from a sort of longish stuff, okay, which requires knowing about the time spent at a frequency. Okay, so maybe I'll say something about it tomorrow. Okay, yeah. Otherwise, I can do folded spectrum. Yeah, so then in that case, so thanks. Yeah, so I'm assuming that here I knew what's a wild type. Okay, so therefore I said 0, and Sally is pointing out correctly. So this is called unfolded spectrum. Otherwise, I will say, okay, with half probability 0 is a wild type, or half probability 1 is a wild type. So its shape changes, correct. It's basically this object, repeats on the other side. That's it. Okay, so I'm using, I should say that clearly, unfolded. Yeah.
I'm a bit confused. So earlier, I think I understood when you wrote f as a function of both n and time. But now,
so correct. Thank you. Yeah. So I'm assuming that this process has been running for a very, very long time. Things are coming, things are going. So therefore, here we will again have a mutation drift balance.
I see.
Because mutations will keep coming, and drift will take them to fixation and so on. And if you take the statistics f of xt, it actually does become independent of time.
I see.
Okay, so if you write down a diffusion equation and you put dt equal to 0, so that's what is basically done to get that answer. Yeah, thanks. Okay. Okay, so it's a bit heavy, but I will want to show you formulas tomorrow. Okay. Okay, so let's go ahead a bit more and now talk about selection. And you will hear a lot more from Sally, but I will do some very basic stuff. Okay, so our favorite model, right, Fisher, again. But now, let's ignore mutation for a second and just drift and selection. So we again have our A1s and A2s, same way as I said earlier, but A1 has a fitness 1 and A2 has a fitness 1 plus S. Okay. So what is the meaning of fitness and all? I'll come to that in a minute. And S could be 0, in which we call them neutral. S could be positive. Then in that case, A2 is beneficial and S is negative. Then we call them deleterious, right? So all of you know that. And as you expect, just if there's no mutation, again, fixations and extinctions would happen, correct? How would the trajectories look like? Yesterday, neutral trajectories were looking like this. And as Mike was pointing out, P prime is equal to P, the average value, right? That's what will happen. But here, if I started with whatever value, it might do like this, or like this. It'll increase if S is positive and decrease otherwise, okay? So therefore, these are fixations and extinctions are possible. And I will just write a formula for you. And then we will try to understand the formula. So from diffusion theory, so again, when I tell this answer to people who are not experts like you, when I say, oh yeah, deleterious mutation, it's a bad mutation, it can also spread. They are like, it's bad. Why would it spread? You know, this is again the naive expectation. Because we are thinking deterministically, we are not thinking of fluctuations. So the point here is that if you ask what's the probability, I mean, you guys of course know now, probability that A2 fixes, so that even if it is deleterious, there's a chance that it fixes. If it is beneficial, there's a chance that it gets lost. And this is a famous formula again due to Kimura, given by this expression. Don't worry too much. But I just write for you because you'll be seeing this again and again and again. What it's saying is that if the selection is positive, then in a large population, okay, so I should say that, if selection is strong, what does it mean, selection strong? You saw a strong mutation already, right? Strong compared to drift. Right? So strong selection means NS is large or 2NS is large for Shannon 1. In that case, the fixation probability is 2 times S. So it's a very famous formula and I will derive that. This is what you already know, 1 by N. So sorry, I forgot to say, single A2 fixes, 1 A2. Okay? Okay. Otherwise, as you expect intuitively, deleterious mutation has a probability non-zero, but a tiny probability of fixing. Okay, and this exponential, as I said, is a fast changing decaying function. Okay, so this one we learned. This is difficult. This requires knowing diffusion theory, which we are not going to do. But this is not so difficult to derive, and thanks to Mike, he already introduced to you recursion equations, and Sally will be doing a lot more of it. So I want to do that calculation because it's a famous calculation by Haldane. Okay, so let's do that. So one more process. By the way, you're seeing this word again and again, process, Wright-Fisher process, now branching process. I mean, again, you know, do you understand the meaning of this word process? So we always use it with stochastic processes, general class of models, which just comes under this umbrella of stochastic processes. Something about changing things randomly in time. That's what I mean by process here. Okay, so what I want to do is just derive this famous formula. Okay. So here are the assumptions. So I'm thinking of a large population of A1s in which a single A2 is introduced. And this large population is so large that I can just think of it as infinity. Okay, it's very, very large. I mean, it's really large. And then there is a single A2. which has a fitness 1 plus S. And I don't know right now whether S should be positive, negative, or 0. It's some 1 plus S. Okay? Yeah. And what we are going to do is to track only the mutant population. So here we have this A2, right? Generation 0. They're all A1s. It's in a sea of A1s. And there's a single A2. And okay, for simplicity, I'll also assume that A2 produces none or 2 offspring with probability P0 and P2 respectively. Okay, so the probability that produces 0 offspring is P0, and for 2 is P2. Okay, so we have this single mutant at A2 at T equal to 0. What can happen in the next generation? What can happen? Yeah, either it produces 0 offspring or none. Okay, so it produced 0 offspring. End of the line. Right? What's the probability for this? For this event? No, P0, yeah. Correct. Okay, but it could have produced 2 offspring also. Right? Okay. So the quantity I want to look at is, okay, should have written somewhere. Okay, let me define it here. QT is the probability that A2, single A2, is extinct by time t. That's the quantity I want to look at. And I will write down a recursion equation. Recursion equation simply means I would like to relate what happens at time t to just 1 generation before. Okay, so that's the kind of recursion equations that we will write down. Okay, so we want to look at this. So Q0, well, it's not extinct, of course. So therefore Q1 is what? So it's extinct by 1 generation is P0. What about second generation? How should we construct this process? So either this happens or this could happen. So I want to know the probability that by second generation, there is no offspring. There's no A2. How could it happen? So let's just do this one. This Q2, if you understand, then we are basically done. So can you sort of think about it and tell me? So the probability that there is no A2 left till by second generation. P0, yes, plus, but P2 means 2 offspring are produced. And, no, you're almost there, yes, but both of them should die. Right? So therefore, this is 1, but T equal to 2, this is dead, right? That's the P0. Right? It died in the first generation. But what if they had 2 children? So then, yeah, okay, let me remove this one. Yeah, tell me, say that again. Yeah, after P2, again P0. Okay, so what we would like is to write it in terms of the previous generation's answer. Okay, so let me repeat this and then let's see if it makes sense. Okay, so this is A2, this is A2. But you see, this A2 is not very different from whatever happens to this A2 is not different from whatever happened to that A2, in the sense that this can also produce either 0 offspring or 2 offspring. So I'm assuming here that things are time independent and so on, the environment, okay? So this A2 is not different from this guy. It's fate, in the sense that, it will behave the same way, except if, so therefore, if by second generation, nothing happens, then this A2 should die, and this A2 should also die, right? So therefore, I will write the answer and see if it makes sense. P2, and they should die in 1 generation. Both of them. Does this make sense? So no offspring was produced. So that's how you're dead with 2 generations. Or 2 offspring are produced, but each of their lineages should also vanish. But that's like repeating the same argument for this guy. This is not different from the fate of this guy, right? I mean, it's characteristics, not fate. Characteristics are not different, but except that this guy has to die in 1 generation. So this block is being repeated over here, right? So, but this had 2 time steps, this had 1 time step, and both of them have to die. So therefore, Q1 into Q, and two are offspring are produced, and both of them die. So this is an assumption, and it's a good assumption. It's saying that these lineages are independent. Does this make sense? So I think it takes time, little time to digest it. So, yeah. Yeah, I think I should write it. This is O. Oh, I'm sorry, this is OR. Either that can happen or that. This QT, I should write it better. Okay, let me write it here. So QT is the probability that A2 dies extinct by time t. By. Yeah, that's QT. So we wrote Q1 and Q2. Try to digest it, see. And if you digested it, you should be able to tell me Q3. And in general, QT. It's just repetition of the same argument. So the idea, the key point here is that whatever happens here is repeats here, but with a one lesser generation. Okay? So think about Q3. And don't try to do each of them. I mean, we cannot do it for Q100th. So I'm not trying to write each of them. So I'm trying to write a recursion equation here. I'm trying to relate Q2 with what happens to Q1. Q3, I will try to relate to Q2. So don't try to write all the probabilities. Of course you can do, but it's perfectly, and that's a good thing to do, but do it at home. It's actually a nice exercise to try. Okay, but right now we'll try to move on. Q3. Okay, I'll write it and you tell me whether it makes sense. So I'm saying it's the same story. Q3 means it had no children, and in the second generation, this guy, in the first generation, it had 2 of these, but these 2 are like that guy. But now to die by 3, you have only 2 steps left. Okay, so I think it'll take some time. So think about it at home. So in general, we have this recursion equation. Which relates the extinction probability by time t to just 1 generation before. Yeah, okay. And we are interested in getting that answer, 2s, the famous answer. So that's the fixation, eventual fixation probability. But you know, when we are drawing these trajectories, sometimes they will go extinct at 100 generations, others maybe take 10 generations. So nobody is waiting at the end of the universe, but that's the question that we're asking today. But in principle, you can answer the extinct by time t. But that's not what we'll do today. Okay, so I'm going to take t to be infinity, which means qt is not different from qt minus 1, because t minus 1 is same as t, if t is infinity, right? So therefore qt becomes q, there's no time dependence left, and therefore q is equal to p naught plus p2 times q square. Yeah? Everybody has seen this kind of equations. What are they called? Quadratic equation. Wonderful. I think we do it in 10th standard, but we forget. So that's another reason I want to do, because this is a nice problem, because even if you've forgotten your school math, it doesn't require a very high level of math. So no differential equations, no nothing. Just the 10th standard maths. If you've forgotten, I strongly recommend go and look at it. Okay, so we have this quadratic equation, but it's useful to actually write it for the complementary probability. And for the fixation probability, which we're writing is P0 plus P2. Okay, you can write it, but okay. I think I want to say something else first. Okay, so this is in terms of number of offspring. What has that to do with fitness? We said fitness is 1 plus S and blah, blah, right? Okay, so the meaning of fitness is this. So fitness is the average number of offspring produced. You see, when I was drawing yesterday, no, sometimes the one offspring, some two, same guy had, right? So fitness is the mean number of offspring. For the distribution, that means when you can have either no children or 2 children, what's the mean? 2p2, right? 0 into p0 plus 2 into p2, correct? That's how we calculate mean, right? Right? And that is the meaning of fitness. So that's what is 1 plus S. Also, either you have 0 children or 2 children, so p0 plus p2 is 1, right? So we can, write everything therefore in terms of S. Okay, so sit with your mathsy friend and work it out. It's not difficult. Okay, so if you plug it in, everything, I will just give you the answer. Then for small s, we will get 2 answers here. So this you have to work out. It's, before sleeping today, go home and work it out. So you'll get answers like 0 or approximately 2s, s small. Okay, so it's saying that the probability of eventual fixation that's given by, it has 2 solutions, either 0 or 2s. How do I decide? Which one would you take? There are 2 answers.
It's 1 minus q.
What happened? P is 1 minus q, yeah, that's, I erased it. So that's P equal to 1 minus Q. Q was extinction. Yeah. So which one would you, which one should I choose? On what basis would I decide? The 2 answers, right? It's not a unique answer, right? We got 2 answers. When we solve this quadratic equation, remember they have 2 solutions. And they can be different in general. So how do we decide? So again, what's your intuition? So it's a very large population of A1s, right? And I said S could be 0, positive or negative. So which solution would work for it? Which one should I take? Okay, let me ask 2S. Can I take it when S is negative for a deleterious mutation? Acceptable? So I'm saying as S is negative, can the fixation probability is okay, minus 2S? Why? Why isn't it okay? Correct, it's not okay. Why? No, it's minus 2S, huh? Minus 0.1 probability. Yeah, probability can be negative. It's always between 0 and 1, including 0. It's because, it's a number of successes divided by sample space. It's always between 0 and 1, right? How can it be negative? So this answer is not acceptable when S is negative. What about S equal to 0? Both are same. So whether you take this one or this one, doesn't matter, right? Okay, so I'll take this one for S. So if this is not possible, so for S less than 0 and S equal to 0, that is deleterious and neutral, this. And if S is positive, okay to take this, answer is there anyway. So beneficial. Yeah. This makes sense. This is giving me 0 fixation probability for neutral and deleterious mutation. But that's not what I told you there. This is a famous calculation by a famous guy. I don't know, maybe he's wrong. What do you think? Should we accept that or trash that theory? Yes. That's, yeah, population size is not also, yeah, it is very large. Yeah. Sorry? Yeah, it is finite. Yeah. So, yeah, go on. Yeah. So if population size is very, very large, infinitely large, you can check this will not work. The branching process, which is what it's telling us, right? Because if it is very, very large, there are no fluctuations. The fluctuations are the ones which are helping the deleterious mutation and neutral population. When you see it first, you do not expect neutral population or deleterious mutation to fix. Right? That's a deterministic assumption, deterministic theory, which assumes that the population size is infinite. And that's what I'm starting here. Okay, so this is our deterministic expectation, which is consistent with over there if I take an n to be very, very large, infinitely large. In that case, no, it will not work. Otherwise, we will get this S positive, for which the fixation probability is 2S. Okay. Okay, so I think I've spent far too much time on small stuff, but it's okay. Okay, so I had a plan to discuss more models, but I think it's just probably too much, and we have 20 minutes left. So I see, so I'm thinking of doing some other exercise. Let's do some activity. Everybody has a coin in their pocket. I like coins. Everybody has a coin in their pockets? Oh, okay, borrow from your friend. I want to toss a coin. So when I toss a coin, what's the probability of getting a head? Huh? What? 0.5, how do you know? Why is it 1.5? Why is it 0.5? I want to measure the probability of getting a head for the coin in my pocket. How would you do it? It's not half. It's not half. To get half, you have to do infinite number of experiments. It's not going to be half. I can guarantee that. So, okay, so activity. Okay, let's stop this. Let's toss a coin.